In this lecture, we're going to look at how heat impacts the rate of a reaction. Um, and so, in general, when we're thinking about heat and reaction speed, there's sort of a common set of intuitions where heating a reaction will often make the reaction go faster. And by go, I mean, proceed. The amount of product that's formed per unit of starting material increases per unit of time. Okay, so everything has a time element when we're talking about kinetics because we're talking about speed. Now, this is a little bit different than thinking about an endothermic or endergonic reaction, where you have to continuously input energy to get the reaction to go towards product. Okay, now we're talking about speed. Which means something a little bit different than thermodynamics, which is, again, how energy is transferred about a system. Just in general, heating will make the reaction proceed faster. And then conversely, cooling will make the reaction slower. So cooling the reaction makes the reaction proceed more slowly. Okay, so that's a really nice set of intuitions. It doesn't always hold. There's some really interesting kinetic phenomena or reactions, excuse me, where we will actually see the reaction slow down as you add heat. But let's look at why this set of intuitions, I guess, is fairly useful. And that has to do with, well, before we get into it, let's remind ourselves what temperature is. So sort of recall that temperature is the average kinetic energy of a system. And this is a fairly this is a good explanation if you want to be a little bit more precise. So it's the average kinetic energy of the molecules of a system or in a system. So the molecules or chemical components, the atoms, however you want to define it, it's the average kinetic energy of how, that is like how much on average each of those things is moving. So with that definition in mind, we can start to think about how heat impacts kind of a reaction. So heat will increase the kinetic energy. That is, adding heat will increase the kinetic energy of a system. That is to say that if we add heat or add temperature, then the average kinetic energy or the kinetic energy of the molecules also increases. So more heat equals more movement of our molecules. Now, a reaction is generally the collision of a few molecules. Okay, sometimes it's the breakdown of one molecule, but if you have some reaction A plus B goes on to C, in the reaction, and this is just a common reaction, or just a very generic reaction. A and B aren't things. It's not B for boron. It's just, this is just saying hypothetically, if we have two molecules, 1A, 1B, you get it. We're going to mix those together to form a product C. In this reaction, A actually collides with B, and they arrange themselves into a transition state. And that transition state is going to have some very interesting structure. I guess it would be a low entropy state because it would be so highly ordered. So its free energy generally increases quite a bit. But anyway, we arrange, and generally bonds are breaking, so things are unstable. So the enthalpy also becomes less negative. Anyway, both those things bring delta G up and make things a little bit higher in energy. So they form a transition state, and product C emerges. And C could be a few molecules too. We could have A plus B go onto a few different molecules, but the same thing happens. The point is A and B collide, they merge, they're kind of moving around, and then they cannot react and form C until they crash into each other. So A collides with B. With this in mind, if we have an increase in temperature, we then have an increase in kinetic energy, which is kind of energy due to movement. So when we say molecules or a collection of molecules has higher kinetic energy, what that's saying is they're moving more often, which leads to an increase in molecular motion, which then leads to an increase in collision frequency. So as the molecules spend more time moving around, they're more likely to collide. If we have a collection with trillions of A and trillions of B, and they're moving a lot more frequently, the probability of A colliding with B to form an appropriate transition state structure is higher. And so more temperature, more kinetic energy, more movement, more collisions, more reaction. Okay, so that's where that intuition kind of comes from. As you could do the exact opposite for cooling. As you cool things down, you decrease movement, you decrease kinetic energy, you decrease collision frequency, you decrease the likelihood of a reaction actually occurring. There's another way of looking at this, and that is the Boltzmann frequency distribution. So the Boltzmann frequency distribution looks like this. And it's often just called the Boltzmann distribution. Now, this is a frequency distribution, and so if you've taken statistics, you might be a little bit more comfortable with something like this. But in a frequency distribution, we have some parameter along the x-axis. In this case, it's going to be temperature, which is which we've talked about is directly proportional to kinetic energy. So I'll put that in parentheses. In some units, it doesn't matter if it's C or K or F, some degree of temperature. Okay, so we've got temperature / average kinetic energy along the x-axis, and then along the y-axis is going to be, if you haven't seen this before, it's a little bit strange, it's called frequency. So this is kind of a graph where, yes, it has a curve, and the curve looks like this. But what that curve really represents is a collection of data points, where if you look, something with a, if you look how many of these things have a temperature right here on the x-axis, there might be 1, 2, 3, 4. Well, according to this graph, we're just stacking these right on top of each other. This is kind of like a bar graph of frequency distribution is. So the y-axis is the number of things that have a certain temperature. So we have temperatures, temperatures, temperatures. They can kind of stack on top of each other. I want to get rid of those. But that's what this is. This course, started clicking redo. What this is this is this depicts the population of molecules with any particular temperature. Now, in statistics, you would use some sophisticated mathematics to show that what you can do is show that half of the population exists on the left and right, and the sophisticated mathematics would show that the line that cuts 50% on one side and 50% on the other side is somewhat to the right of the highest part of the hump. And that's because this is a skewed distribution. So 50% of the molecules have a population to the left of this number, and 50% have a population to the right of that number. That's an important line to kind of know what that means. It's not important exactly where it is. It's a little bit to the right of the hump based on how this is skewed, but 50% of the molecules are to the left and 50% are to the right. And specifically, the mathematics would use an integral to show that the area under the curve is equal on either half of this distribution. Okay, now what I want to also add, that's a really helpful data point, that 50% left, 50% right, because what this line represents then is the average of our distribution. It's the middle point where half are above and half are below. So what does this yellow line or this yellow highlighted line represent then? This is the average. And it's the average temperature of our collection of molecules. This is read by the thermometer. So this is read by the thermometer, okay? So our average is that point where 50% is to the left and 50% is to the right. What makes this a little bit awkward is the distribution is skewed. So the shapes on either side don't look the same, but we have a longer tail to the right. And so that's going to then allow us to see that that's how we get a greater area on that right, excuse me, an equal area on that right side is that tail is so long. And that tail is something I want to pay attention to. So that tail is what I'm referring to is like this portion here that actually kind of goes on for quite a while. I mean, molecules are finite things, so we have to stop eventually. But that tail does drag on quite a bit. Now, what I'm going to do is I'm going to insert a line, and I'm just adding this point and saying for our arbitrary reaction of A plus B goes to C, this is the activation energy. The difference in energy, if you go back to our energy diagram, is this is the difference in energy between the transition state free energy and the starting material free energy. So I'm just throwing this line in there. This is the activation energy. It's far to the right on the x-axis, okay? So it is a higher energy than the average kinetic energy of the system. Okay, so in the previous plot, the activation energy is higher. I'm going to color that again just so we're all on the same page, is higher than the average kinetic energy, which again is the temperature. Remember that yellow line, that yellow point is the average of our plot. That's the average kinetic energy of this entire population of molecules. That's the temperature of that population of molecules. Okay, so we can observe, I want us to first observe that the average kinetic energy is higher than the temperature. The purple line is higher than the yellow line. But you notice I did shade in an area purple to the right of that activation energy. There is a small population, that is the frequency or the number of molecules that have an energy greater than that activation energy is small, okay? If you look at the shaded part of the graph, that is a smaller region of the graph than the rest of the graph. Like maybe we say 5% of that entire graph, 5% of all of the molecules of the population have an energy above the activation energy. So there's a small population of molecules with an energy greater than the activation energy. An energy greater than the activation energy. Okay. And they are shaded. That region of the graph is shaded. So this frequency distribution allows us to see that there are some molecules with a greater activation energy for our particular reaction. And what this means is these molecules can do the reaction. These molecules can do the reaction. Okay, good for them. They're in a small part of that distribution. The total number of molecules that have the energy capable of doing that reaction is small because the population of the shaded area above our activation energy is not very big. But let's increase the temperature. Okay, so I'm going to draw another frequency distribution where I've got temperature. and I've got frequency. Okay, now the thing that doesn't change is our activation energy line. But what we're doing is we're going to increase the temperature. Now the temperature is a little vague because the temperature is also the x-axis. So maybe kinetic energy is a better label. But I want to change or increase the average kinetic energy of our system. So maybe originally, let's see, it was pretty much halfway. So the original temp. Now again, the temperature is the average line. And what we're going to do is we're going to shift it over. Now, if you recall, that means that we need to draw our curve so that the hump starts heading downward, because the average, by definition, must have 50% area or 50% of the molecules to the left and 50% of the molecules to the right. And then we're going to, whoop, my hand slipped right there. So I've shifted the temperature over to this position. I can now highlight this line as my new average. And again, the average kinetic energy of the system is the temperature. And what's exciting about this is the activation energy doesn't move because that reaction is just fixed. We've increased the temperature to bring our molecules closer to that kinetic energy required for the reaction to occur. Do all of the molecules have the kinetic energy for our reaction? No, definitely not. But a much bigger proportion of those molecules do. The shaded area increased. Shaded area increases. That means that more molecules can do the reaction, because more molecules have a kinetic energy that's greater than the activation energy. So the activation energy doesn't change. By increasing the temperature, we shift the average kinetic energy over. If we shift the average kinetic energy over, we're going to shift the entire distribution of molecules over to the right, increase the number of molecules that are have a higher kinetic energy than that activation energy. Okay, you could do the exact opposite, and I would encourage you all to practice it. Let's cool the reaction mixture down, shift that kinetic energy, I don't know which way is left or right, but shift it towards a lower x-axis value. That's going to shift the shape of the distribution. That hump is always to the left of the average line, the bigger hump is. And if we do that, we could show ourselves that the shaded region of our graph, the number of molecules with a kinetic energy higher than the activation energy will decrease. Cooling slows down the reaction because we don't have enough molecules with the proper kinetic energy. Heating increases the speed of a reaction because we now have more molecules that have the kinetic energy capable of doing the reaction.